We're going to talk about correlation. So there's a lot going on with this lesson. So you may recall that to determine the equation of the LSRL, your calculator minimized the sum of the squares of the residuals. So remember the least squared regression. The smaller the squares, the better the line was. The small, I guess I just said that, but it's the next sentence. So the smaller the sum of the squares, the closer the data was to the line of best fit. However, the magnitude of the sum of the squares depends on the units of variables being plotted. Therefore, the sum of squares cannot be compared between different scatter plots. It is not a good way to compare the strength of various associations. Today, you will investigate a better way to describe the strength of an association by using correlation coefficient. So let me pause real quick and set something up and then talk about that. What we're saying. Let's say I had scatter plot A and scatter plot B, right? I have some little data there. So if I said, hey, which one is closer to the actual, right? Which predictions look more accurate? You would probably say B, I would think, I would hope, right? Because those residuals are very small compared to over here. But what if I said, oh, by the way, the scales here, these are in miles and these are in millimeters. Well, now all of a sudden, even though this looks further away, these are actually way smaller. So it becomes difficult to be able to compare because, of course, you know, in this example, if we missed by, you know, that might be 10 miles right there, which looks like nothing on our scale. But of course, 10 miles is way more than here, which is, you know, I don't know, what, 15, 20 millimeters. So we can't always go by the scale. That's really what we're talking about here. So when we look at correlation, we're going to compare things. It's a measure of how much or how little data is scattered around the LSRL. That is, if you have already plotted the residuals and decided that a linear model is a good fit, the correlation coefficient R is a measure of the strength of the linear association. It does not have units, so it is useful no matter what the units of the variables are. So we can compare here, and maybe we'll see that this has an R of 0.95 and this has an R of 0.7. So even though these are actually technically larger distances, it gives us a comparison to say that this has a stronger correlation than A does. And again, I'll probably come back to this in a second, or I shouldn't say a second, but at the end of the video, if I remember to kind of drive that point home, because I know at this point you're saying, I don't know what an R of 0.7 or 0.95 means, but hopefully by the end of this video you will. All right, so again, a couple of important things here. We already have run the residual plot and decided that a line is a good fit. You don't do the correlation coefficient if a line's not a good fit. So we've already run the LSRL, we've already run the residual plot, we've decided the line's a good fit, and now we're going to investigate even further by saying how strong is that relationship or how strong is our correlation between the two. So what it asks us to do is kind of play with this tool here, and you can see it gives us the R down here. So I'm just going to start moving these points around, and you can see the impact that it has, right? So look at that one. I'm negative here, but I'm close to zero. Negative, close to zero. Now all of a sudden, I was going positive for a second. There we go. Now I'm positive, but close to zero. What if I move it over here? Look at that. It's really close to -1. So kind of interesting that the closer it is to an exact line. Oh, I just had it. I was trying to get it to. When it's an exact line going downhill, we're going to be at exactly -1. I'm not having much luck anymore. All right, but what happens if we go the opposite? What happens if it's positive? You can see now it's really close to +1. So some kind of interesting things going on here. And what we're going to find is this, and I kind of have this website open. Two things are going to be recognized with correlation, with R, right? If the R, if it's positive or negative, if it's positive, you're going to get an uphill line. If it's negative, you're going to get a downhill line. The second thing is 1 and -1, right? The absolute value of 1. If it's +1, you'll have like perfect line, right? If it's +1, we're actually going to be able to say that our lines are perfectly lined up. I don't know why there we go. I know I kind of took the cheater way out, but I'm having a lot of trouble getting exactly 1, which is really annoying. So down 1, whatever. I mean, you either get it or you don't. Got it. Yay! All right, so these points exactly go in a line. So that's going to be like a positive 1. And you can see as I deviate a little bit from that, it's going to go to like a positive 0.7, which is what we're looking at here. And then as it gets even more random, right, as it gets even more random, we get closer to like a 0.3. And that means it's not a super strong correlation. Whereas negative, it works the opposite. It can go from -1 to -0.7 to -0.3. And you'll see in the both in the middle is 0. When R is 0, it's essentially chaos is really what we're looking at. So again, here's what it looks like when it's +1, if it's +7, 0.7. So the strength of the association. If it's a positive, right? Again, the positive negative just tells you if the line goes up or down. Typically, I think the book is going to tell us 0.7 is what we consider strong. So a strong association is going to be 0.7 or -0.7. Medium will be like 0.3 to 0.7, and then like small to weakened association will be 0.3 or less. And again, that's as an absolute value. All right, so moving along here. Parts A through C, use your calculator. What happens when we have 1? It's exactly straight up and down. What happens when we have -1? It's exactly up linear, exactly down linear, and then chaos. And let me pause this real quick. Actually, I don't need to pause it. I'm pretty pleased with what I've already said. So now we should be able to look. We're going to match these things. So here's the thing. I know this has to be a positive R. Actually, I guess I need to go over here. Ugh, so frustrating. I can't write on this. So I know that this, I'm going to match -0.9, -0.6, +0.1, and +0.6. So when I look at this data and this data, I know this has to be the 0.1 and the 0.6. So I think this is the 0.6 because it's got a stronger correlation. This must be the 0.1. It goes up, but it's essentially chaos, right? So there's a little more order to this one. Some of these points are much closer to the line, so it's a little more order. I know that this has got to either be -0.9 or -0.6. Well, in this case, it's going to be -0.9. That's a very strong association. My line does a great job of predicting the actual points, whereas over here it does less of a good job. There's definitely more scatter, so I'll say that's a -0.6. So when we match those up, that would be what they match up with and why. So in problem 4.1, you completed an investigation that helped Ronnie use a viewing tube to see a football game. Sample data is shown. We have the LSRL. So it says determine the correlation coefficient and is the association strong or weak. So the first thing I'm going to do is I'm going to do this in this calculator. So I will turn it on. I will clear the memory 712, and I will input this data, which I'll take a pause for. Determine the correlation coefficient. Is the association strong or weak? Well, I don't even know how to do it in this calculator, so I'm going to look at my cheat sheet, and you can see R and R squared are down here. I'm going to turn the diagnostics on. So I have my data already put in. I'm going to hit second catalog down here at the bottom. Second catalog. By the way, you can see where it says A, that's the green alpha key. There's a shortcut here. You can see the little green letters. I know I want to choose diagnostics, so if I go to the one that says D, which is right here, it'll just jump straight to the D's. It's just like a shortcut. It jumps from letter to letter. So you can do that, or you can just use the arrow. It doesn't matter. But I'm going to go to the one that says diagnostics on, and this gets screwed up all the time. Enter. My diagnostics are not on. I have to hit them again. When it says done, now my diagnostics are on. Again, this happens all the time where kids just hit diagnostics on, they don't hit enter again, they don't turn their diagnostics on, and they get confused. So what I need to do is go through what I have been doing. I'm going to go stat calc. I'm going to run linear regression. I am going to go vars, y vars, save this function, and calculate. And look what happens. Because I turned my diagnostics on, it gives me my R. It also gives me R squared, and we'll worry about R squared later in the chapter, but for right now, R is all we care about. 0.997. Well, that is positive and very strong. So again, if we go ahead and look at that, I'll turn this plot on and look at this graph. I would expect to see a positive line that is very close to the data. And you can see that's exactly what I get. So no surprises there. All right, so how would I do this in Desmos? Well, what I'll do is I'll go here again. I will input a table. So I'm going to pause here while I input this data and go through the steps again. I didn't do the checksum on this, which I should have done. So I'll go calculator, 2 variable, run L1, L2, and 816 for L1, 122.4 for L2. So great. Okay, so again, I want to determine the correlation coefficient. So I put my data in. Again, I'm just going to go y1 tilde and then it's mx1 plus b, and there we go. They do the R and R squared for me already, so it's 0.9972. So again, we get strong and positive. Again, two things: is it positive or negative, and is it strong or weak? This is positive and it's strong. All right. Describe the form, direction, strength, and an outliers association. Again, strong and positive. I would say no outliers. You already know a graphical way to determine if the form is linear by looking at the residual plot for the data. A mathematical description of direction is the slope. A mathematical description of strength is the correlation coefficient. Mathematical descriptions for outliers will be dealt with in a later course. So yeah, it's kind of weird. This book doesn't really talk about outliers, which are kind of interesting. There's a bunch of different ways to determine outliers, but we'll leave all that for your other teachers. So describe the form, direction, and strength of the viewing tube data in more mathematical terms. So again, the form is linear by looking at the residual plot. So do we think that this is linear? So let's look at the residual plot, and we'll zoom in a little bit. Again, we can actually change the scale on this. So I'll go from -1 to +1. So, I mean, it goes up and down and up and down. So I would say no pattern. If this point was up, then I would say there's a pattern. But this one, for me, it breaks it up. I guess you could make your own argument there, but I would say no pattern. And again, if we want to go here to get the residual plot, I'm going to go stat edit up to the top. I will run my residuals. And then I will change my stat plot to L1, L3. And graph it. And then I'll go zoom 9 to get a better look at that. And again, you can make the argument that there's a pattern there. I would say no, because it goes back up and back down, but some people will probably say yes. So the form, I would say linear is a good fit. Description, I'm sorry, direction is the slope. So I would say, what are we getting? 0.13 y's for every 1 x, so 0.13 width of view for every 1 distance from the wall. And the strength, the correlation coefficient, I would say strong and positive. All right, so an E-tool is available to help you explore the correlation coefficient further. So we can open this E-tool and kind of mess with it. I don't know, does this allow us to sort of change some of the data? So you can see just sort of changing some of these numbers around, it's going to have an impact. What if I put like -10 and sort of flattens it out? If I put a few -10s in there, I think it's going to drop everything down and sort of change my slope here. So anyway, you can see that there's some changes there. So it's kind of up to you if you want to play with that thing. Again, I hope that we recognize that the closer it is to 0 and chaos, that means it's not very reliable, and then the more it looks like a line, we know that it is either 1 or -1. and somewhere within those parameters. Okay, so that always goes back. So I'm at 422. So I think that is where we're at here. So just make sure you recognize kind of what's going on here with what we talked about these and how to make them.